Okay, so I'm going to make a hard dividing line in SQL Server 2005, everything prior to that and everything after that. The reason is the world changed in 2005 for SQL Server. Everything went different. So we're going to look at everything prior. And by the way, all of those solutions that were available to prior to 2005 are still available, and in some cases or another may still be a great option. But I don't want to focus a lot on the past. So we're going to talk through these a little bit quickly. But they were log shipping. And I was trying to find out the other day, because I really couldn't remember whether log shipping was available before replication or vice versa. And I don't really remember. But so I'll just say log shipping came first and replication came second, and I may be wrong on that. But log shipping was the first one that I kind of think of anyway. And then replication, and then failover clustering. So log shipping. Log shipping works like this. We have two computers. Do you like the way I chose these computers with floppy disks in them? That's how old this was. They actually used floppy disks back then. Right? So I purposely found a picture of a server with floppy disks in it. Now, you would take a backup of your database, and this was a one-time event. You would back up your database, and then you would move that copy over that file, that backup file, over to the other physical server and restore it. So that at this point in time, my two computers for at least this one database were exactly in sync. Then you would schedule a transaction log backup. Now, if I talk about some of these things like transaction log backup, and those aren't familiar to you, you don't know what I mean by that, please ask a question. I'll be glad to give a quick idea, but I'm kind of assuming since you're here, these types of things already make sense to you. So we would create a schedule, maybe every hour, every half hour, twice a day, whatever you wanted to. You'd create the schedule, and at those times, the transaction log would be backed up and would be copied, that file would be copied across the network to the other server, which would then restore the transaction log backup. So we always had a standby machine. However, this second server was always in restoring mode. In other words, it couldn't respond to any user requests, but I had a backup of my data. I had my actual literal backup, but I also had a hot standby so that all I needed to do if my first machine died was to do a quick restore. So my end user here would sit down and would connect to the first machine and do his or her queries. If something went wrong with that first machine, the process looked like this. First thing we had to do was to bring my secondary machine, the one that had been receiving the log shipping devices, and restore it completely. So it's no longer in restoring mode, but it's in multi-user mode. And then we would have to go over to my end user and say, oh, we had a problem. Why don't you disconnect that query, that session, and reconnect to this other server with a different name? That was perfectly fine if you had 10 users in the universe. When you started having very many users, that became very problematic. Log shipping has evolved since then. There are certainly better things going on in there, but that's the way it started off. And quite frankly, it was kind of a worthless solution. It has some places that it still makes sense today. And that has to do with the timed nature of the restores. There are environments where I work where the ability to constantly have these two computers communicate with each other is not there. Some of the environments I work in, They don't allow connections except for at timed periods, once a night, well, maybe 2 o'clock every morning or something like that. And so the ability to time this is great. But here's the major drawback to this with log shipping is my second copy of the data is always out of date. How much out of date it is depends on how often you do those transactional log backups and restores. But it will always, 100% of the time, be out of date. So at any given time, if my first server dies, I will have lost data, period, end of story, no getting away from that. I can reduce the amount of loss, but I can't eliminate it. So log shipping was historically, if not the first, one of the first solutions. It was not a great solution, but at the time, it was a lot better than what we had. Then came along replication. And just like log shipping, replication has evolved over the years. Initially, quite frankly, it was a horrid solution. It didn't work. It developed a really horrid reputation. And it was always just one way. One server would replicate its data to the others. So I couldn't update my data on the other servers. That was in the past. It's no longer true. We now have several different forms or installation methods of replication. But the way it stands today is each one of these computers can accept read requests and write requests, and they immediately replicate that data to either one other partner, or in the case where we'll be talking about, they would replicate that data to all other partners. There are built-in mechanisms for dealing with what happens if I change this data in this place and at that place at the same time. We're not going to get into all those details, but those are available and they do a good job. Replication today is actually a very excellent process. But it doesn't do me any good if that's where I stop. I can have all of these servers all completely up to date, never missing a bit of data, but then what does my user do? Which one of these computers should my end user connect to? So we introduce something else, and we call it, what we introduce is a network load balancer. Now, Windows has network load balancing capabilities built into it. Please, if you value your sanity, don't use it. It's not that it's really so bad all by itself, but it's a software solution, and it's never going to keep up with any kind of demand. Go buy a hardware appliance. You can get them from all sorts of companies, Cisco, Barracuda. I'm thinking, my mind's drawing a blank, but there are tons of devices you can buy network load balancer devices from. I used F5 here in the example because I really like F5s. And I have to be honest with you and tell you why I really like them. They're a great product, but they have more blinky lights on their appliances than any other device I've ever seen. And blinky lights just attract me like honey does bees or whatever it does. I love blinky lights. And then they also once gave me a sleeve of golf balls with F5 written on each one of them. I fell in love with them. I thought they were great. So I love F5s. But all joking aside, they are a great appliance, but it doesn't matter which one you use, any network load balance appliance, but make sure you buy a hardware appliance and not use Windows. How that works then, what happens is I have a user. The user wants to connect to an instance of SQL Server to do some querying or some updating or whatever. She will contact DNS and say, what is the IP address of this server? DNS will lie to her and will tell her the IP address is really the IP address of the network load balancer. That request comes into the NLB. The NLB, the network load balancer, then finds the most available server to answer that request. Since the data is being replicated on all of these servers, it just simply chooses which one has the least current load. Different load balancers, and this was how they distinguish from each other, Some of them do just a eeny, meeny, miny, mo, round robin kind of thing. That's a terrible way to go. Others say, well, I sent one request to this computer and one request to this computer. I haven't sent a request to this third computer, so I'll send it next. That's a little different from round robin, but it's not great. Then there are solutions, some of the hardware solutions. We'll take a look at what servers have the fewest number of requests stacked up. That's a big advance. But really the best network load balancers look at that plus the current tax on their hardware. So they may not have a lot of requests stacked up, but the CPU is pegged at 90% and the disk I/O is through the roof. So even though there aren't that many requests, we're going to skip you for now and go somewhere else. Every user that comes in gets redirected to one of the computers, one of the servers running in the background. And the load balancer is configured with each of these computers. The beauty to this solution is its scalability. If I am running a program, some kind of advanced thing, and suddenly I'm looking at my website and it's just trashed and the SQL Server is barely keeping up, all I have to do is go pick up a new computer somewhere, not new, like go buy it, but go grab one sitting on a desk somewhere, configure it with SQL Server, replicate the data to it, and then tell F5 that it exists, and suddenly now you've just scaled from 5 computers to 6 or whatever. And then later when that marketing campaign or whatever goes away, you can scale it back down. It's also nice because in some solutions, each of these computers have to be exactly the same. And from the looks of how I drew this, well, I didn't draw it. Okay, I stole the clip art from somewhere. But from the looks of the clip art I stole, it looks like they're all the same, but that's not necessarily true. I could have really powerful machines next to dogs, and it's fine because any one user is going to be communicating with one server at a time. So when this yellow session gets started, the network load balancer makes sure that it only talks to that computer number 2 until the session ends. The next time our user comes in, she might be connected to a different computer, but whatever computer she's connected to, that session is static in the sense of it doesn't change unless something horrible goes wrong. But let's say our blue session here is communicating with that last computer and it dies, catches on fire, dies, horrible, painful death, whatever it is. In that case, the network load balancer sees requests being unanswered and will suddenly redirect those requests for the blue user to a different backend server. So replication is a really fascinating and great way to go. And it's also one of the cheaper solutions and one of the more scalable. I actually, even though this is one of the oldest solutions available in SQL Server, it's one of my favorites. Okay, let's change gears and let's talk about Windows failover clustering. Windows failover clustering has been around since, I don't know, the mid-90s, something like that, somewhere around there. And it's really not a SQL Server thing, it's a Windows thing. And it's an ability that Windows Server has to have 2 nodes, and if something goes wrong with one, fail over to the other. SQL Server just rides on top of this. Now, SQL Server was the very first application Microsoft ever created that was cluster aware, and I think it may be one of the very first applications, at least that still exists today, that ever was cluster aware. But here's how it works. I have 2 computers. They must be exactly the same. I mean, we have to get down to like the CPU. Both the family and the model have to be the same, and the stepping of that CPU should be the same. The microcode revisions really ought to be the same. Doesn't have to be, but the family and the model certainly does. The number of cores, the amount of memory, the type of network card, the number of network cards, number of disks, all that stuff has to be exactly the same. In fact, so much so that Microsoft now publishes what's called an HCL, a hardware compatibility list. And that hardware compatibility list has always existed for Microsoft operating systems. And it's always been one of those things, oh yeah, I've heard of that, but nobody pays attention to it. With Windows failover clustering, if you buy hardware and try to install failover clustering on it and it's not on that HCL list, the installation process just simply says, nope, I won't do it. So it is a very particular solution, and that hardware, as you might guess, ain't cheap. They know they're on the HCL, they can charge what they want for it. So it's a fairly expensive solution. So I start off with 2 computers, and they are exactly the same. Since they are exactly the same, I don't care which one is active and which one is passive, but one of them has to be active and one of them has to be passive. Now let me explain that I'm showing you Windows failover clustering at its simplest. It gets way more complex than this. We can have active, 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 passive, active. We can have up to, I think the latest number is like 16 nodes. That can get way, way more complex than this, but that doesn't help us understand it as a SQL availability option. So I'm not going to go get into all that. So at its simplest, I start off with 2 physical computers, and one of them I choose to be active and one of them I choose to be passive. I've named them Node A and Node B because in the parlance we talk about nodes. So I call them Node A and Node B. I'm not very good at coming up with creative names for things. So we chose Node A to be active and Node B to be passive. Since they're both exactly the same, it really would make no difference, unless those 2 computers are in separate geographical areas. Ideally, with a failover cluster, they'd be sitting in the same rack right next to each other. But I don't live in an ideal world, and I know you don't either. So we often have them maybe at racks away on the other side of the data center, maybe in different data centers across town, and maybe we participate in what we call geo clustering. You know, Node A might be in Toronto and Node B might be in Shanghai. And that's fine. There are limitations, I should say, with that. There are problems we run into, but it's perfectly fine to do geo clustering. It wasn't always, but it is now. So we chose Node A to be active and Node B to be passive. If this was geo clustered, if these were in different locations, we would choose the active node to be the one that was closest to the most number of users or consumers of the data. But in this case, if they're going to sit in the rack right next to each other, it makes no difference which one is which. Those 2 computers share an external hard drive. That external hard drive could be an external iSCSI disk. It's unlikely anymore. In the early days, that's what we used. But nowadays, almost exclusively, that external SCSI disk is going to be a SAN, a storage area network. That SAN, or that external disk, whatever it is, will contain your data files and your log files. Now, if you've ever taken a class from me, your ears are perking up because you're saying, wait, the data files and the log files on the same disk? Jeff always preaches against how bad that is. And yeah, I do. And yes, it is that bad. And that's one of the reasons I'm not a big fan of failover clustering. But let me hold off on my opinions till we get it thoroughly understood. But my data files represented by the MDF and the log files represented by the LDF file all exist on the same physical disk. I know what a lot of people are thinking because I've heard it 100 times before. Yeah, but my SAN is going to protect those files. Okay, if you believe that, if you really, really believe that, I have real estate in Northern California I'd love to have you take a look at. If you really believe the SAN can be trusted to always protect your data files, then there are a lot of places I can take you. But even more importantly, so what? My SAN may be able, let's pretend it can. It can perfectly take care of my files. That doesn't really help me, because I just installed a very expensive failover clustering situation and I didn't protect my data. The SAN does, but my solution doesn't. We'll get into that. I'm getting ahead of myself. So I have these two computers, one's active and one is passive. On the active node, SQL Server is installed and the services are running. On the other node, the passive node, SQL Server is installed and the services are stopped. In both cases, they are set to manual, not automatic, but but on the active, the services are started and running. On the passive, they're stopped. Now, each of those computers has their own network cable, their own network access, their own IP address, all that kind of stuff. And typically, the two computers communicate to each other via your regular network, which works very well if they're on the same switch. They're in the same VLAN, for instance. But if they're not, like if they're geo-clustered and for some reason they can't be on the same VLAN, we can use what's called a heartbeat network. This is a dedicated network to nothing but these two computers or however many nodes you have. And it's a heartbeat network, and it's where the two computers or nodes constantly tell each other, I'm alive. So 6 times every second, node A says to node B, I'm alive. 6 times every second, node B says to node A, I'm alive. And it starts to feel like, remember those old annoying Verizon commercials where the guy was walking around going, can you hear me now? Can you hear me now? It's like that. So that heartbeat network can be a single point of failure. It's really not that big of a deal though, because I still have my regular network. And if I'm really worried about it, I could install 2 heartbeat networks. I think that's kind of overkill, but it's certainly a possibility. And for the price of 2 network cards and 1 cable, you're what, $150 into this now, and you've got you've eliminated a single point of failure, a SPOF, and so that's a good thing. Normally, I don't see heartbeat networks installed though. All right, last thing that we do, not last thing chronologically, but one thing, this all happens at the same time, is we have what's called a resource group. That resource group has its physical existence on that shared drive. It's physically a file there, but it is loaded into memory and running on the active node. It contains lots of things, but for our purposes, the only 2 important ones are the name of the instance. Notice I didn't say the name of the computer, the name of the SQL Server instance, and the IP address. Once again, just like with replication, if you were to go look up in DNS, it would say that this instance named, my production CRM or whatever it is, its IP address is 10.10.0.96. In reality, there is no physical device anywhere in your network with that IP address. It's a lie. It's a virtual IP address, if you will. But when my end users go to connect to it, they contact DNS, and DNS gives them that IP address. And so it is interpreted by the active node, and all the requests go to it. It writes its data to the shared drive. It reads from the shared drive. Everything's running fine until that day something goes wrong. Whatever that something is, it could be anything. It could be a hardware failure. It could be an instance failure, a corrupted binary file. It could be any number of things. It could be that the network card took a dump. You know, who knows what it is, whatever it was, node B stops hearing from node A. And it lets a second go by and says, wow, that's 6 times I haven't heard from it. Lets another second go by. And at the end of the 3rd second, it says, that's it. Node A must be gone. Because if it was alive, I would have heard from it a bunch of times. At that point, we end up with why we call this failover clustering. That resource group fails over and starts running on node B, which has been the passive node. At that same moment, the services on the first machine are either shut down or they weren't able to be shut down at all because the server may be completely gone. But if they are running, they're turned off, they're stopped. And the services on what has been the passive node, node B here, are started. This process is what accounts for almost all of the delay when a failover occurs. SQL Server services are not very slow. They start up pretty quickly, but whatever time it takes your services to start accounts for almost all of the time it takes for the failover to occur. Microsoft published, and this is amazing to me, published that failover for, they weren't talking specifically SQL Server, but things in general, would take between 2 and 12 minutes. That's ridiculous number. It won't take you 12 minutes. It won't take you 2 minutes. First time I saw that, I had to check and say, wait, is that 2 or 12 seconds? Because, you know, 10, 15 seconds is what I would expect to failover to be. So I suppose, like as an example, Microsoft Exchange, the services take about 1.5 years to start up. They're just terribly slow because there are so many of them. And so they can take quite a bit longer, but SQL Server is pretty quick. When it fails over fairly quick. The services start up quick. The resource group fails over, and now those clients which were connecting to 10.10.0.96, they're still connecting to the same thing. It's just that we moved that over to another physical device. Does that make sense? Any questions about that? Okay, let's talk about, just quickly, we'll go over this in detail later, but while we've got this picture up here, let's just talk a little bit about the weaknesses of a failover cluster. Number one, we have a huge single point of failure right here in the disk. Yes, I know, it's a SAN, it will never fail. Yeah, right. SAN is taking care of it, great, but my SAN was already taking care of it, and my buying an expensive failover cluster solution didn't add anything to that. It didn't add anything to protecting my data. So once again, the question of what am I protecting here? In a failover cluster instance, what I'm protecting is the availability not of my data, and I'm certainly not protecting the data itself. I'm protecting the availability of the instance, and that's all I'm protecting. Now, I don't want you to get me wrong. I don't think clustering is a horrible solution. I just think it's a horrible solution for SQL Server. Okay, so at this point, the services have started, and node B goes from having been passive to being active. Now it's my active node. At some point, node A, we're going to fix the problem, presumably. And people ask me quite often, well, at that point, should I fail back to node A? And my answer is why? Why would you? The two pieces of hardware are the same, the data's the same, everything's the same. There's no reason to fail back to node A, but you certainly can.